Everybody, let's begin the introduction to kinetics. So this is lecture 1, and my name is Rodrigo Albuquerque. The movies, so I'm just recording all lectures, and they can be found, the links to the lectures can be found here at www.labsuperchem.com under teaching. There are many other links to other lectures there involving, including molecular modeling, and other topics as well. In this section, I will summarize what I'll be teaching. I will identify supporting materials. Let's consider why kinetics is of importance. I will introduce the rate law, define the rate constant and its units, and I will introduce zero, first, and second order kinetics. So the 7 lectures I will be showing here, they will include reaction orders and their determination, rate laws, molecularity and complex reactions, collision and transition state theories. In supporting materials, I would recommend, first of all, we have this book of Peter Atkins, Physical Chemistry. It's a very good book. But if you want to further read, you can read this book here, Physical Chemistry, A Molecular Approach of McGuire. So this is a very nice book discussing very depth of different subjects of physical chemistry, including kinetics. And this other book is Elements of Physical Chemistry. Is another level, is not such a high level as the McGuire, but it gives some insights, useful insights to kinetics. By the way, this W perhaps is a P, so I need to check this, so you can check. So how fast are chemical reactions? They can be very slow, like the Rost formation. So we have here this layer. The red layer is due to the formation of iron oxide, which is a very slow process. You cannot see it happening. It can happen in many years. But reactions can be much slower than this here. As you see, for instance, the transformation of diamond into graphite. Diamond is a kinetically stable state of carbon, while the graphite is the thermodynamically stable. So here, in fact, the diamond, we can call it a metastable. It's not the most thermodynamically stable. And graphite is more thermodynamically stable. What happens is that the reaction is so slow that we cannot realize, we don't see it happening, even hundreds of years. So we need here thousands or millions of years to see it happening. So some other reactions, as you see here, can be much faster, like catalytic decomposition of hydrogen peroxide. Here, this guy is adding a catalyst, I think adding iodine, and then the iodine catalyzes this reaction, releasing oxygen. And some reactions can be even faster, like the decomposition of sodium nitride. As you see here, this solid is inside airbags, and they decompose into nitrogen gas and inflates this bag, the airbag. And it's so fast that we need to see this in slow motion. So understanding how fast a reaction, so what are the factors controlling the speed of reaction, the kinetics. So it's very important because then you can control, you can manipulate reactions, you can change a little bit the conditions to get a slower reaction, a fast reaction, and this helps you to get applications, as we see here, for instance, this airbag application. And there are many more applications for kinetics. So first, how to measure concentrations. For gases, we can measure the pressure or the volume. For instance, the airbag inflating. In the beginning of the process, you can just get the volume, and afterwards the pressure increases inside. But there are different ways to do this. We can use also a spectrophotometer and a clock. If we see a solution changing color, for instance, the solution is blue and slowly is changing into transparent. So some reaction is occurring inside, and we can monitor the UV's absorption, as we see here. Sorry. So here we have initially a blue solution, but some reaction is happening. The blue colored chemical is decomposing to give the products, and products are transparent. So we can just add a detector here. So we shine light here to measure the absorption of the solution. We get a detector here, and we see how fast this process occurs. And then we can now plot the absorption, the intensity of absorption against time in order to get a concentration. So if we get absorption, we use the Beer-Lambert law to get a concentration. And then we see that when we increase time, the concentration of the reagent is in the beginning high, and it decreases. In the beginning, it decreases very fast, and then it decreases slowly. And the product in the beginning, the concentration is very small, so in principle there is no product in the reaction vessel here. And then the product is formed, and in the beginning is formed very fast, and then the formation gets slow until it gets a stationary state here, where the concentrations are now constant. We can use also flow techniques. We have reagent A here in blue, reagent B in green part. And so both reagents are inserted here very fast. And we have a spectrometer seeing the light absorption, so monitoring the light absorption along different positions here, so that it's possible to see in the beginning. So if this place is being monitored in the beginning of this chamber, the time is close to zero, while if you move this part more to the right, the reaction occurred already for some time. So you are monitoring the right side of this axis here, and this can be used, this arrangement, but you can also put a stopping syringe here. So there's a stopped flow technique where you have the reaction, and at a given volume this stops, and then you can get the absorption, and then you can calculate the concentration of the species involved, of the reagents and products. You can also have flash photolysis. Now you can imagine you shine a fast light pulse to the sample. The sample is going to absorb light and can also emit light. And then we make a time resolved detection. So we see how light is emitted if the system is luminescent, how light is emitted upon time. So there's a time resolved detection. And there are many ways of measuring concentration. And now let's talk about the rate of reactions. So here we have the reagent transforming to product. In the beginning, as I showed before, concentration of the product is very small, so here is zero, and this concentration changes very fast in the beginning, and then changes slowly, more slowly in the end. In the reagent, the concentration begins very high, and now, upon time, this reactant is being decomposed and transformed into product, so that you achieve a stationary concentration in the very end. The right side of this plot is studied by thermodynamics. So in thermodynamics, we don't want to see how fast this equilibrium was achieved. We just need the equilibrium concentrations here of the product and of reactants, for instance, to predict rates and equilibrium constants and so on. While in the beginning, we have different speeds of formation or decompose of the products of the reactants. And this part, the left side of this plot, is investigated by kinetics. So if we get any point here, we can calculate the gradient or the slope of the line passing through this point, of the tangent to this point, which is the dashed line. And here we've calculated infinitesimal variation of the product divided by infinitesimal variation of time. We have a positive gradient or slope, as you can see here. So if this angle is 45 degrees, for instance, the angle with this dashed line with the horizontal line. So if this is 45 degrees, the tangent would be 1. So there's a positive quantity. And this rate is the instantaneous reaction rate. In this case, actually, the instantaneous rate for the product formation. If we get now a point in the reactant curve, we can now calculate the slope. The slope in this case is negative. The point going to the left to the right. The line is going down. Okay, so this quantity is negative. So the slope is negative. And you can see that in the beginning, if you take, for instance, this point here, if you put the point in the beginning, the slope is much more negative in the beginning, and it gets less negative upon increasing the time. And this slope, if you take this point and put here in the very end, so the slope would be 0, because the dashed line would be horizontal in this case. So the module of this gradient is the reaction rate, can be defined as reaction rate. So in this case, we have a negative quantity. In this case, we have a positive quantity. But reaction rates are always positive. That's why we use the module of this quantity here. So reactions are faster in the beginning and gradually become slower, as we see here, because the slope is larger in the beginning, for instance, of this blow curve, and then becomes smaller. And since reaction rates, I'm calling Vt, are always positive, we need to add a positive sign here, which is the same as showing the module here. So we add a positive sign before derivative of concentration of products with respect to time. This is going to be positive anyway. Or we add a minus sign here because this quantity is negative. So if we add a negative sign, now we have a positive V, because reaction rates are always positive. And now the units of the reaction rates can be in mole per liter. Mole per liter is actually molar of this big M here. Molar per second. Molar per second, or mole per decimeter, cubic decimeter per second. So these are common units for the reaction rates. Let's do now a task. So task 1 is a very simple task. A certain reaction was monitored to get this instantaneous rate, the composition rate of the reactant. So the concentration of reactant dt in the beginning of the reaction, the very beginning. So the best value that describes this quantity is, which of these options would be the best one? So you can now stop, think about it, and then you play again to see the answer. And here is the answer. So the option B is correct, because the most negative value is expected to be observed in the beginning of the reaction. Just remember, what's being monitored is the concentration of the reactant against time. So the slope, if you start looking at the reactant, the slope is negative. And in fact, in the very beginning, the slope would be very negative. The most negative value that is available here is this here, minus 0.8 molar per second. Now, rate of reactions. Let's compare the different reaction rates. So here we have 2 moles of nitrogen oxide reacting with 1 mole of oxygen gas, giving 2 moles of nitrogen dioxide. So you see that 2 molecules, if you think of this as a molecule, 2 molecules of nitrogen oxide would react with 1 of oxygen to give 2 molecules of NO2. This in fact is not a molecule because we are showing the aggregation state, which is gas. So this is in fact 2 moles. So it's a very large quantity of NO reacting with a very large quantity of O2, but it's just 2 moles of NO reacting with 1 mole of O2, giving 2 moles of NO2. So the first thing we can realize is that consumption of NO, of nitrogen monoxide, is 2 times the consumption of O2. So at every any step here, you are decreasing the amount of NO by 2 and decreasing the amount of oxygen by 1. So the consumption of nitrogen oxide is actually 2 times the consumption of oxygen. So you can show in this way. First of all, we are talking about reactants. So both are reactants, which means we have a positive sign to get the reaction rates. A negative sign. So we have negative, negative, because this fraction is already negative. Since reaction rates are positive, that's why we add here a negative sign. But the consumption rate of nitrogen oxide here on the left side is 2 times the consumption rate of oxygen. This is shown here by this relation. Now the production rate of NO2 is 2 times the consumption rate of oxygen. So every 1 mole of oxygen that disappears, 2 moles of NO2 are formed. So that the production of NO2 is 2 times the consumption of oxygen. And we would show this in this way. So take the last part, this part of this expression shows that the production of NO2, which is shown here with a positive sign, is 2 times the consumption of O2, shown here, consumption rate of O2. Now, the consumption of NO, so the consumption is precisely the same, consumption rate is the same as the production rate of NO2. So every time 2 moles of NO are consumed and 2 moles of NO2 are formed. And that's why we have this part here is the consumption of NO is equal to this part, which is the production of NO2. Now, how can we express this, get a single value to get the reaction rate? So first of all, we can divide these rate expressions by 2, which means we would be using the respective stoichiometric coefficients in each denominator. So the stoichiometric coefficients are 2, 1, and 2. So this would lead to the final expression of Vt. So the expression of rate of reaction, okay, sometimes I say reaction rate or rate of reaction. This is given by minus 1/2 of the consumption rate of NO, which is minus 1, the consumption rate of oxygen, which is plus 1/2 of the production rate of NO2. So what we see here is that the green numbers, they are just the same as here. 2, 1 here is not shown in the oxygen, and 2. So there's a way to express the reaction rates. In all cases, reaction rates are positive quantities. And they show a relationship between production rates and consumption rates, if you wish. So you can use this expression to get relations between those rates. So usually we don't use the plus sign or 1 divided by 1 fraction. So we don't have here actually 1 by 1, or we don't have a plus. In general, we forget about this plus here. But all terms here will be positive anyway. Now let's do a second task. Consider the general reaction A plus 2B giving 3C plus D. So I'm not specifying any state, which is a gas or anything. So let's just think about molecules happening. Molecules are reacting here. A plus 2B giving 3C plus D. So how could you write the reaction rate Vt in terms of the individual consumption and production rates of all reactants and products involved? So you can just pause now here the video, and then when you have solved this, you play again to see the answer. And the answer is C. As you see, this is a very simple task. First of all, we see the consumption rates of A and B, which are reagents. So A and B are reagents. That's why we have a negative sign here before, so minus and minus. And the stoichiometric coefficient of A is 1 and of B is 2. So we have in the denominator 1 and 2. That's it. And while the products are C plus D, actually 3C plus D. So products, we should have a positive sign here before the production rates. We don't need to show the positive sign. And at the denominator here and here, we would show the stoichiometric coefficients 3 and 1. So you can see here 3 and 1. And this expression also shows the relation between consumption rates and production rates of different species here in this reaction. Now let's talk about the rate law. The rate of reaction Vt that you already know how to get can also be written using the rate law, which can only be determined experimentally. So this is a very important point. If you want to know the rate law, you need to do experiments to get the experimental rate law. So let's suppose we have this reaction here, A plus 2B giving 3C plus 1/2 of D. So Vt is proportional to the concentration of reactants at time t. Yeah, we didn't talk about this t, but every time I show Vt, of course at time t, raised to a simple power. So Vt would be proportional to the concentration of the reagents, A and B, raised to a power like raised to the power of 2, to the power of 3, like in this case here. So we don't know who is x, who is y. X and y could be actually 1 or 2 or 0 even, but Vt is proportional to the concentration of A to the power of x multiplied by concentration of B to the power of y. So these are the reagents here. So this is a way to begin to discuss the rate law. So now if we add a proportionality constant here, k, we can add an equal sign here. Now the reaction rate is given by this constant, rate constant, multiplied by concentration of reagents to the power of x and to the power of y. So this expression here is the so-called rate law. It's a very important expression because it allows you to know what's the reaction rate at different times. If you know the concentration of A in concentration of B at different times, at the same times, of course. And if you know the force, the rate constant, K. So here again is the reaction rate, you know already. K is the rate constant, which depends on the temperature. In general, we assume is constant in a very narrow range of temperature, but in fact it depends on temperature. If you increase temperature, this can change. The concentration of reagents or reactants A and B, and the exponents here are the orders of the reaction with respect to A or B. For instance, in this case, the order of the reaction, of this reaction with respect to A is X, and the order of this reaction with respect to B is Y. And the global order of this reaction would be X plus Y. Now the units, as I said before, the reaction rate is in mole per liter per second, so it's molar per second. It's a concentration divided by time, so it's a molar per second. The rate constant actually depends on X and Y, because the concentrations, they have always this molar per liter, so mole per liter, so it's a molar concentration. They're always a concentration, so if you have X equal to 2, you would have mole square divided by liter square liter. So the units of the rate constant actually depends on X and Y. And X and Y themselves, they have no unit. And note that 1 liter is 1 decimeter, 1 cubic decimeter, or 1 dm3. So this is very often used also, this unit. Instead of showing mole per liter, you would see mole per decimeter. Now, we don't know the units of the rate constant, but if we isolate rate constant K from this reaction, we just would have Vt divided by this product here, divided by concentration of A to the power of X, concentration of B to the power of Y. So if I know X and Y, I know the units of concentration, which are easy, is molar, for instance, and the reaction rate would be molar per second. I just add here to get what's the unit of the rate constant. Now let's do a task again. So a student has determined experimentally the rate law for the reaction 2A plus B given C, and found experimentally, as always, Vt equals K multiplied by the concentration of A to the power of 1 multiplied by the concentration of B to the power of 1. So what are the units of the rate constants in this case? So we have many options, and you can solve this now, and you can pause the video. When you solve this, you just play again to see the answer. And the answer is A. Because if you isolate K from this reaction, you see that K equals Vt divided by concentration of A multiplied by B, because the exponents here are 1 and 1. So Vt has units of molar per second, and the concentration to the power of 1 molar multiplied by molar. So that if you do this operation, you find that K, so this should not be capitalized, sorry, so this is a small mistake, so this should be a small k, it's not capitalized. Mole minus 1, liter second minus 1. So this is the correct unit for specifically this rate law, which was experimentally calculated for this reaction. Now let's see the difference between the zeroth, first and second order kinetics. So let's take this simplified equation, so this reaction, and this reaction is described by this rate law. So the kinetics of this reaction is described by this rate law. where the overall order of the reaction is given by the sum of x and y. And this sum could be 0, so we would have a zeroth order reaction. If we just had 0 in x and 0 in y, we have that Vt equals k. This is shown here, which means Vt doesn't depend on the concentration. Vt is constant during the whole reaction. So this is a special case shown by this expression. Now, if x plus y equals to 1, we would have this possibility. So the exponent is 1, and the other of b would be 0. So x equals to 1 and here is 0. Or the contrary, x would be 0 and y would be 1. So in both cases, we have first order reaction. And in this case, Vt depends only on the concentration of A or on the concentration of B. Now, x plus y could be 2, for instance. There are many other possibilities here. I'm just showing some of them. So Vt, in this case, if x equals to 1 and y equals to 1, we would have the first case. So the order of this reaction, the global order, so overall order is 2. So I have a second order. But the order of this reaction with respect to A is 1. Okay, so this reaction is first order in A, but the overall order is 2, with the sum of the exponents 1 and 1. We would have also this other case, where we have Vt equals K and concentration of square of concentration of A, or square of concentration of B. In all these cases, we have an overall second order reaction. Now, this first lecture was short, just to show some basic concepts of kinetics, very introductory kinetics. And the key points are shown here. So reaction rate is given by this. We have Vt is minus the consumption rate of reagents, or is given by plus production rate of products. This happens because Vt is always positive. Since this quantity here is negative, we need to add negative sign here, as already discussed. The units are mole per liter per second, or mole per cubic decimeter per second of the reaction rate. Okay, so second, we just saw how to write down expressions for the reaction rate based on the consumption rate of reagents and on the production rate of products. And we have seen how to write this down. For reagents, we use a minus sign. For products, here we use a plus sign. And the respective stoichiometric coefficients 2, 1, and 2 are shown in the denominator here. 2, 1, and 2. So Rate's law is an expression that relates the reaction rate with the concentrations. So it allows you to get reaction rates as a function of concentrations, or to get concentrations as a function of the reaction rate. So if you measure reaction rates, you can predict concentrations at a given time, or if you measure concentrations at a given time, you can get reaction rates at that time. X and Y are called order of reaction with respect to A or B, respectively, and the sum of X and Y is the overall order of this reaction. The rate laws are only obtained experimentally. And now we have some examples of expressions for the reaction rate for a zeroth order, which is this here, so the reaction rate doesn't depend on concentrations. The first order, the reaction rate depends on the power of one concentration, could be A or B. And second order, we are just showing one of